I hereby open the session. Dear doctoral candidate, the Board of Conferral of Doctoral Degrees of Utrecht University now grants you the opportunity to defend your dissertation in public. First, I would like to introduce one guest from outside Utrecht University, and that is Professor Koenraad from the Technical University of Eindhoven. We greatly acknowledge your willingness to participate and help us in the scientific task of this committee. Now I call upon Professor Koenraad to start the opposition.
Give you a congratulations with writing a very interesting thesis, which I've read with pleasure. And as you can expect, I have a number of questions for you. And one part that really interested me is tip preparation. I'm an STM specialist myself, and I know how much time is lost, as you write, in getting the tip that you want. So, to speed up or to lighten that task for my PhD students would be a great achievement. In your thesis, you spent a full chapter on that, and I would like to know whether you have really tried this procedure in practice, in the sense that you have created a system where you prepare a tip, check it with your neural network, and then actually gave the system the opportunity to improve.
Hooggeleerde opponent, thank you very much for the compliments on my thesis. You ask about whether I've implemented the procedure that I outlined in chapter 3 of my thesis. The answer to that is yes. We, in our group, we've actually, in collaboration with our IT support, we've connected with our STM in such a way that we can load in a neural network model, so that we can load any model that we've created for testing. Then as it scans, the image that we've just scanned gets input into the neural network. Then it will do some action on the tip based on what decision it has come to. So if it's sharp, it won't do anything. If it sees like a blurry image, it will crash the tip.
Mm-hmm. Okay, thank you. A very interesting option could be that you actually learn how to regenerate or tune your tip. So what do I have to do to get a sharp tip? Does the system also allow you to find those parameters?
The interesting thing about that is, well, for a start, to get a good tip, you may well know that you have to just repeatedly crash the tip into the surface, and it's quite a random procedure. However, I've seen a paper where they crash the tip into the surface very gently until they see a few units of conductance going through the tip. And they do it several hundred times, and they found that after that, then they did get a good tip. I suppose because when you dip the tip into the surface and then you drag it out slowly and repeatedly and very gently, you apply some force to the end that pulls the atoms down. So there is that way. Other than that, we could, if you have some sort of interface with your STM, you can discover, and if you have it automated, you can do tests to discover what type of procedure creates what type of tip in the end, and maybe you can find some relationship.
Yeah, indeed, and that is what I'm after, because we would like to start with experiments where we have a magnetic atom on the apex of the tip, and we would like to know what magnetic spin state or spin orientation we have there, and if possible, to prepare that state. Do you think that your approach could offer us some help and guidance there?
I think it would, as long as you can determine a difference in an appearance, for what your tip functionalization is. So if you have a magnetic atom at the end of your tip, and then you see the difference in the surface when you image it, because there's always a convolution between tip and surface when you measure an STM image. Then, of course, you can train a network to distinguish that from any other tip.
Okay, thank you very much for those answers. I would like to move on to chapter 4, and especially to page 62. And there you introduce the quantum corrals that are the building blocks for your networks. And I have a number of questions there. I read, for instance, that in your quantum or your 2D quantum corrals, magnetic quantum numbers are not present in 2D systems. I'm really surprised by that remark. Could you explain that a bit more to me?
So, when you do the calculation for a three-dimensional atom, you have some extra component, you have an extra degree of freedom, which isn't present in the 2D case. So that introduces an extra quantum number into the calculation. So then it's possible to have just this L quantum number without having the M quantum number.
Well, if I look at it, and I work in the field of semiconductor physics, you can make a quantum well in a semiconductor material. Are you familiar with that?
Yeah.
Yeah, and that's a two-dimensional system. And then with a FIP, I can cut out a small structure, or I can create another way to confine in the X and in the Y direction. So out of the 2D system, I make a 0D system. And your quantum corral, the structures that you have here, to me seem 0D structures. So that also have a confinement in the Z direction. So why not have this magnetic quantum number as well there?
For your 0D systems, well, I'm sure there would be some degree of freedom which allows you to have. There must be at least something, because you would have wave functions. You would have your electrons trapped within still. So you would still have some quantization, which would lead to some quantum numbers.
Sorry, go on. Yeah.
As for what particular ones you would get from a 0D system, though, is it not only the N quantum number? I'm not entirely sure.
Yeah, and okay, for me, it's also surprising that you lose your PZ state, or where that comes from.
The PZ state?
Yeah, you say, well, as we show below, PX and PY like states do emerge in rectangular corrals. So where's the PZ state?
I don't mention it because we just use the 2D system, and then we just assume it's confined from the surface. So there would actually be some state, because there's some confinement from below and above, from the vacuum above and the surface below. So there would be confinement. But
then I come to the idea of a 0D system.
I see.
Yeah. And then my question is actually, how many electrons do you confine in such a quantum corral system that you are looking at?
I think that on the surface we have just this sea of electrons, and there's a certain density of electrons per nanometer squared on the surface. I think it's like, I don't remember the exact number, 1, 2, or 10. I don't remember what the exact number was. So when we confine them, we could sort of say that we can calculate how many electrons would be in there, but I can't tell you what that would be off the top of my head.
But if I would take you to figure 4.3, where you show the IDV measurements, and you sweep the voltage, and if you're at negative voltage, I would presume that you're looking at filled states. And when you look at positive voltages, you look at empty states. That for me would indicate, if I have a true 0D system, that I have 2 electrons in the S-like ground state that you see at the lowest energy, and I think 4 electrons in the P-like states. Is that a correct conclusion?
I think you do have the correct conclusion, because in the 2D system, except for the ground state energy, the S-like orbital, there is a 2-fold degeneracy for every level above. That's what you get when you calculate it for the 2D system. So I think you're right that there would be, just for a purely 2D system, nothing more, there would be 4 electrons because you have spin up and spin down as well.
Correct. Yeah, and this is how I get to the 6. And then my final question, if there is still some time, Mr. Chairman.
If it's a short question, it's okay.
Yeah, then I'm a bit surprised in this respect. So if you say one quantum corel contains 6 electrons, and I'm going to connect these quantum corels to each other, that you talk about 2 body interactions, say in chapter 6. Would it not be 6 electrons interacting with 6 electrons? Or am I really looking in the wrong direction?
As for the number of electrons that are interacting, sorry, I only know that there would be some density of electrons at the surface.
Okay.
And we can find them, and there is some interaction. They bond with each other into a lattice, but I can't say how many.
Okay. Thank you very much for your answers. I'm pleased with this.
The discussion will be continued by Dr. Fritz.
Dear candidate, I would also join into the compliments about your thesis. I have to say what I found really impressive was both the number of things you did, as well as the fact that you really nicely combined theory and experiment in your thesis, which made the job a bit easier for me as a theorist to ask questions. So, but like the first question I would like to ask is a very generic one, and probably I'm not even asking the right person, but at least you made that choice to use the word. So I'm asking you. So you're using artificial quantum matter, and like if I look at all the things you did, those things are very real. So why do you call it artificial and not designer quantum matter?
Zeer geleerde opponent, thank you very much for your compliments. I very much appreciate them. As for why we call it artificial matter, it's simply as opposed to matter that exists already in nature. We've really constructed it by hand. So that's why I name it artificial matter. Maybe in theoretical physics you have another definition, which I'm not aware of.
No,
okay.
We don't. Okay. I was just curious because for me, designer somehow seems more natural. But okay. Anyways, so let me start asking about the artificial graphene. So essentially on this copper surface, you built this graphene or this honeycomb lattice, which has properties in a lot of ways like graphene. So are there, like, if I look at the system, are there also differences with actual graphene? Like, or is it just a replica of graphene?
So, for the comparison between artificial graphene and real graphene, you do see the similar features in the band structure, such as the Dirac cone, but the energy scale is different because you have wider sites you have bigger sites, and then we change the on-site energy of each site not we, but the group who did it. So the energy scale shifts. Secondly, because it's only a finite lattice that you can build artificially, and not just a huge one like a whole sheet of graphene. You could see some finite effects, like, for example, you can't make a real band structure because you don't have some continuous number of K points in your band structure.
Okay, and how is it, for instance, with things like, let's take spin-orbit coupling? Is it the same as in like actual graphene, or is it very different?
Well, with spin-orbit coupling in our systems, you would need to introduce maybe a different substrate, which is formed of some sort of heavy element, to perhaps induce a spin-orbit coupling so not using copper but using lead or something else. Then you may induce some effect with spin-orbit coupling. So you can.
Sorry.
So maybe you can tweak it in that way.
Okay, but like if I understand correctly, like the main appeal of using copper is that it has this like perfectly circular, like Fermi surface, which is very narrowly confined to the surface. Would that be like the same with lead, or is it different?
With lead, I think it's different. So with lead, we confine a surface state on copper. Because it has a surface state. With lead, I don't believe it does, but you can put adsorbates on which can form the lattice itself that you want to build. So you can build an artificial lattice with adsorbates on top of the lead, for example.
Okay. So another thing I was wondering is like, I mean, it's nice to build graphene like artificially, but there's actually a pretty good version of it, which is graphene. So, is there anything you think which is particularly like, or for which this approach of depositing atoms is more suited, as compared to say the real thing? So,
for the benefit of making artificial lattices in this way is that the artificial graphene, that was one of the first demonstrations of using carbon monoxide on copper to create some sort of artificial matter. It had been done before with quantum drums, but in the artificial graphene case, they wanted to see whether they could emulate the properties of graphene just by using this artificial platform, and they did. But then the benefit that comes after that is that because you can build any structure you like, you can build things that don't exist in nature or are not known to exist in nature, or you could test new theoretical models. So that's the benefit of this platform.
My feeling is that like there's actually quite some activity in this field of strain engineering, and my feeling is that for this technique, this is quite feasible because
could you repeat?
Strain engineering, like many people think about strain engineering, or maybe also things like twisted bilayer graphene, and it seems like these things come very natural with your setups. The only problems might be like system sizes, I guess.
Yeah, so you can induce some strain just by simply the group who made the artificial graphene, they made their sites bigger in one direction and not the other. So then there was sort of like an artificial strain. So you're only limited by the symmetry of the copper atoms because your CO molecules only sit directly on top of copper. And so you just need to figure out where you can place them to create your artificial matter. Other than that, you're not restricted in the shape.
Okay, very nice. I also wanted to ask something about edge states, but I feel like I'm running out of time, so I would rather like to ask you a different question, which is let's assume you had some more time to spend with this machine and with the techniques you have. What would be like your preferred experiment that you would run? Like what would be the structure you would like to build, and why?
There were some issues with one of the experiments that I did, and I would really like it if I could finish that properly and see the effects that we really wanted to see. I'm referring to chapter 6 about the dimerized square lattice.
Okay.
Yeah, I would repeat that experiment.
Okay. So nothing new, just like try to wrap it up properly.
Maybe my mind has gone empty.
Yeah. Do I still have one more minute? Is that correct?
You have one more minute.
Okay, then I will get back to that. So, I mean, you looked at these edge states, and also like you addressed the question, what do impurities do to these edge states? Because one of the exciting properties of edge states is that they're protected to backscattering, and the technique you use is mostly like density of states. Is there any other technique that you could think of, like maybe with your machine, where you could, for instance, more directly, or in a more direct way, show that there's this backscattering which is forbidden or like not allowed, say.
For measuring backscattering, or for measuring let's say the current that flows in your edge state, I think you would need to do a transport measurement, which would require several separate tips, but then you have to look at the very tiny sample. So I don't think that's possible in that respect.
Is it possible to do this, like what people call quantum quasi-particle interference? Quasi-particle systems. It's essentially like putting impurities, doing a real space map, doing a Fourier transform, and like relating it to scattering channels. Is that something
that should be what you just described should be possible, because you can measure if you have an adsorbate on your surface the wavelength of the scattering of the electronic surface state. Then you can Fourier transform it and then find some values of K, and then you can I think make some form of band structure by looking at different energies and different wavelengths. Maybe you can do something like that, but within a lattice, I'm not so sure.
Okay, I think my time is up. So thank you very much.
Thank you, Dr. Fritz. The discussion will be continued by Professor Dijkstra.
Dear candidates, first of all, I would also like to congratulate you with a very, very beautiful thesis. It is very well written, very clearly written, and in particular, chapter 2 was a great pleasure to read, especially for an outsider of the field of quantum materials. So thank you very, very much for such a nice pedagogical review on quantum materials. I've learned a lot, and I really hope that all the theses in the future will have such a nice introduction into these fields. So my first question is, so in your thesis you've worked on artificial atoms, molecules, but also lattices, but they are all basically 2D structures. Would it also be possible to go to 3D or quasi 2D, for instance, bilayers? This was already alluded to by Dr. Fritz, or would it just be completely impossible experimentally, or wouldn't it be interesting at all?
Hooggeleerde opponent, thank you so much for your lovely compliments on my thesis. You make me feel proud. So as for whether you can have three-dimensional artificial lattices, you could think of it in a photonic or optical lattice, but in the systems that we have, that I've been working on with CO and copper, as purely a surface. We're limited to the surface in our experiments.
But can you grow it slightly large, and so a bilayer, for instance, or that would really be impossible?
I'm sure you could think of some sort of system where you layer some form of semiconductor and then etch it away, and then you get layers which interfere with each other in a third dimension. I can imagine that could be a possibility.
Okay, thank you very much for your answer. But let me take you now to chapter 3 of your thesis, where you use convolutional neural networks to classify STM images. And you classify them into 6 different categories: sharp, double, unstable, step country, bad country, and rubbish. Do you really need so many categories? Don't you just want a tip that gives very sharp images? So why do you choose 6? Is it not easier to classify it into 2 categories, one that gives sharp images and one that is just rubbish?
That's a nice question. I think you're right. So you could choose between having there's a benefit of what you just mentioned, just having two categories, good and bad, because all you ever want is to have good. And then, so whenever you see any other category, all you do is crash the tip and then move to a different area, which is hopefully clean. And then eventually you will get a good tip. The rationale, though, for using multiple different categories is so that you can decide different actions based on which category the neural network finds. So, for example, if it's a step country category, you don't need to crash the tip necessarily. All you need to do is to move to a different location and then check the check again. For double and for bad country, you may need to crash the tip different depths if you can figure out what procedure would be best for that. So it depends on what you would like. I think for being more efficient, in the end, it could be useful to have these 6 different categories.
Yeah, thanks. I was also surprised by the huge number of convolutional layers that you use in your neural network. So 16 resulted into overfitting, but still you use 12 convolutional neural networks. So we've done a lot of training also with images, different images, but usually, 2 are sufficient to have a good classification. So do you know what all these layers are doing? Can we learn something from the machine learning? Do we know what are the important filters or features that it tries to extract from these images?
So each convolutional step, each convolution procedure does indeed refer to like a particular feature that it's extracting. So if one convolutional feature is good at detecting steps, then indeed, like maybe you do only need a few. But we have like a reasonably broad amount of different situations that you could come across, also with different tip functionalizations. So as for the number of features, maybe we have a lot, and I'm not sure whether 16 layers was warranted or not. We didn't check using only 2. Maybe it would have worked, but we got good results using this number of layers without too much overfitting of the data.
Yeah, and then so in your convolutional neural network, you use the softmax activation function for the output nodes. So it gives you basically the probability that it belongs to one of these classes. So can you use that information somehow? So if the probability that it belongs to a sharp image is, for instance, very low, is it then indeed very close to, for instance, the decision boundary? And if it is almost 100%, is it far away from the decision boundary? I think you can also use that information because you want to have a tip that makes sharp images, and you want to be 100% confident that it is then really the good tip. So did you use that information?
Yeah, that's a good idea, and we looked into it. So at the end, we get this probability distribution to see which the highest probability is the category that the neural network eventually assigns as its decision. So we would often see just high values, like we would see, for the example that I gave in the image in figure 3.2, it was quite typical that we would see something like 99% for one of the categories. It was rare that we would see something with 50%. And when we did, it didn't necessarily correspond to it being on the boundary of one category. For our eyes, it's quite natural to think, oh, the sharp category and the double category, if you look at figure 3.1, the sharp and double, they're quite similar to each other. But in a neural network, it's not. you're just using pixels and it's just mathematical functions. So sometimes, surprisingly, two similar categories could have quite different outputs, I think.
Is there time for a quick last question, or should I give the word back?
If it's very quick, you are allowed.
Yeah, my final question is, so it is hard to identify sharp and double images. And I think it's because you don't have enough data there. Would it be possible to use a generative adversarial neural network that generates images, and then there's a discriminator that learns from seeing if they are fake or real?
I think it's a good idea to use a generative adversarial neural network, because the thing was, when we have to categorize these images ourselves, and when we do, we can introduce some bias, because when we look at multiple sharp images in a row, then we think if we look at an image which is like slightly less sharp, but actually would be acceptable in any other time, we would think, oh, that's a bad image. Let me put it in the double category. But if we had seen bad country images the whole time, and then we had seen that same double image, we would think it's good. So there's bias like that can be introduced. Also, when multiple people classify the images, bias is introduced that way because people have different standards. So if you use a generative adversarial neural network, if I remember correctly, you have two networks, one which generates images, one which determines what the image is, and they both improve each other over time. And therefore, I think it could be a good idea in the end.
Yeah, thank you very much for a very nice answer. I give the word back in view of the time, to the chair.
Thank you, Professor Dijkstra. The discussion will be continued by Professor van Bladeren.
Dear candidate, also congratulations from me for a thesis that I read with great pleasure. I'll start off with a very mundane and trivial question, but I still was intrigued. The chapters that you specifically wrote for this thesis, like 2 or 3 or 6, don't have an abstract, while the other chapters do have abstracts. You don't like abstracts? What's the reason for that? I think they're particularly useful, actually.
Hooggeleerde opponent, thanks for your compliment, and sorry for not including an abstract on every chapter. It's simply, I suppose it's simply slipped my mind.
You didn't even notice? You didn't even notice? So 3 and 6, which you specifically wrote for the thesis, there's no abstract. Okay.
Yeah, I should have.
No, there is no real reason. That's the answer, no?
Yeah, no, there was no real reason. For the chapters that were published, then I put an abstract. But for the others, I didn't. I'm sorry about that. It would have been helpful.
Okay, then we agree that can be useful. Let's go then to the title of your thesis, Sculpting on the Nanoscale. I actually think that you did more what my hero in physics, Richard Feynman, did when he was daydreaming in his American Physical Society lecture in 1959. I'm aware that you're aware of that lecture as well, when he was daydreaming, what if we could build up materials and matter atom by atom or molecule by molecule? And that's exactly what you've been doing. So I therefore read your thesis with quite a big interest. And so what you actually came to is what is sometimes worded, and you use the same wording in chapter 2 as quantum matter or quantum materials. But you also state on page 12 that is ill-defined. What if you would need to come up with a definition? Let's just say for quantum matter, to make it simpler. What is your definition? What is quantum matter?
My definition of quantum matter would be, then it doesn't have to be artificial. If you just say quantum matter, then it could just be a material which exhibits some quantum effect. Then again, I am aware that that would be most metals because the electrical behavior of metals derive from the quantum behavior of the material. So then I suppose it would be a material that you look at on a small quantum scale, and then you see these small quantum effects. That's what I would define.
Okay, I perhaps don't completely agree with that, but I'll get to that in a few minutes. So you have shown beautiful effects in your quantum materials, quantum matter that you generated for your thesis, but quite a few of those I would categorize as what was expected, like hybridization of orbitals and so. So they're beautiful, but they're examples, but like nothing new to say it in a little bit negative way. What are the new insights that have come out of the structures that you made that were not yet in that category of as expected? So first, what came out of your thesis? And then also quite importantly, what do you think can still be with these systems you can contribute to? That question has already been asked, but I mean it a little bit broader than you answered it before. So what big questions, for instance, that exist in science can these systems still contribute to, perhaps? So first, from your thesis, what are according to you the biggest unexpected results?
Okay, so chapters 3, 4, 5 is a bit unexpected because if you chapter 5 is regarding creating topological insulators, one atom at a time. And some people may have the misconception that for a topological insulator you need something like strong spin-orbit coupling or a strong magnetic field or something like that. But in this case, we made it just by tailoring the geometry of the system. And not only that, but there's something called the bulk boundary correspondence for topological insulators, which says that the number of bands that you find, the number of edge bands, topological edge bands that you find relates to the bulk in some way. But in this chapter, we changed only the edges of our material, and then we could create a topological system or not. So it also depends on the edge. That's what we found there. And chapter 6, we attempted to see interactions in our system. Usually it's not possible because there's broadening and other effects. So we can't see electron-electron interactions. But for chapter 6, we found a way to effectively simulate these interactions. So that's what I contributed in that case. And what was your second?
And if you go daydreaming like Professor Richard Feynman and think where these model systems could be used for to answering some very big questions in science, what could you come up with?
So for these artificial systems in general, people have proposed things like Majorana fermions, which are useful for quantum computing, and other things that are still in the realm of theoretical physics. For this platform, though, there are
many issues with fermions. Do you think you can tackle these with these model systems?
Not with carbon monoxide on copper.
Okay, we agree on that. But then, so that's a good answer. I was actually perhaps expecting or hoping that you would answer something that one of your collaborators, Professor Christiane Moret-Smith, was alluding to, and I'm aware that you probably don't read the Dutch newspaper, the NRC, but this Monday she was in a page-long interview. She was actually speculating that fractal quantum matter systems may give a clue to whether consciousness So you've used neurons to recognize some of your images, but she's speculating that perhaps, consciousness based on neurons, of course, may be related to quantum mechanical behavior. So are you aware of that she's thinking about that and that she's considering like fractal systems that you can make as perhaps relating or to giving an answer to that?
Considering the time, you can give a short answer.
Okay, yeah, I did see Cristiano's thing in the newspaper just by sheer coincidence yesterday, because I was at a cafe. I think I probably have to agree that it has to be a quantum effect consciousness. It can't. I don't think it arises out of.
But then your system with because you can make fractal quantum matter systems, which are rare, could contribute to answering this. That is a very big question, though. Where does consciousness come from?
I suppose, but then how do you measure how do you then measure whether your system is conscious or not?
That we have to ask Christiana, I'm afraid. But thank you for your answers.
Thank you, Professor van Bladeren. The discussion will be continued by Professor Meijering.
Dank u wel, meneer de rector, waarde promovenda, dear candidate. I agree with all my colleagues that your thesis is very well written. I've learned a lot, clear illustrations. It was very insightful. My question is about the first word of your thesis, sculpting. When I teach lectures on nanomaterials, I teach my students that there's two ways of making nanomaterials. One is top-down, where you sculpt away, you chisel away material, like in lithographic techniques, and then you end up with nanostructures. The other way is top-down, where you add molecules together. Now, the way you do it, I think, is a bottom-up approach, where you add molecules to create a nanostructure, and it's not sculpting. So why is the first word of your thesis sculpting?
Hooggeleerde opponent, thank you for your compliments. The rationale for choosing the word sculpting is you're right that we do add molecules to the top of the surface and move them around. But when I say sculpting, I'm referring to the electronic potential on the surface that when we place a molecule, we deplete the electronic states at that point, and then it's sort of like sculpting.
Just away some
charge. Then we're left with the quantum material that we like.
Okay, beautiful. Then a more serious question, chapter 4. And I'd like to go immediately to figure 4.4 on page 68. There you see a very nice agreement between the energy of the ground state as a function of the Corel size, and you can explain it very well. But then you also see for the S1 a feature at 0.24 electron volt, at 20.24 volts that you ascribe to S state. And I think for the S2 you also see an onset of that to S state. And on page 67 in the middle, you promise to say via the infra that there will be more about the 2S state. I couldn't find anything. I was wondering, this splitting between the ground state and 2S state, I expect to increase when your size decreases of your Corel. Could you calculate that splitting? Is there an agreement with the theory? And also, can you measure beyond 0.4 volt to also resolve that 2S state for the smaller structures?
So I'm not sure I fully understand your question. Are you referring to whether? So I have S states which you can measure by placing the tip in the middle of the corral, and then you only see.
Yeah, and then you see for the S1 you see a feature at minus 0.3 volts, but then there's a second feature at 0.24 volts that you ascribe to 2S state.
Yeah.
And I wonder if that splitting between those states, I expect it to increase with decreasing size of your Corel. If you've also compared that splitting as a function of size and compared it to theory, and if you could also measure beyond 0.4 volts to resolve that higher energy feature for the smaller Corels.
So we didn't think of measuring the difference in energy between the two S-like states, but also we indeed wouldn't be able to measure it above 0.3 volts. on the copper 111 surface. So at first, when you're at lower voltage, your surface electrons form this nice parabola for the EK relation, but above 0.3, then you don't have that anymore. Then there's broadening, and then you.
The committee will withdraw for further deliberation. The session is adjourned. I hereby reopen the session. Madam Doctoral Candidate, this committee installed by the Board of the Conferral of Doctoral Degrees has considered your dissertation and has heard your defense. The committee has decided to confer on you the title of doctor. I now kindly ask the supervisor, Professor van Makenberg, to invest you with the honors in traditional fashion.
By virtue of the authority conferred on us by law and according to the decision of the Board for the conferral of doctoral degrees present at this session, I hereby confer upon you, Saoirsé Erin Freely, the doctoral degree to which are attached all rights and obligations towards science and society, as laid down by law and custom. Do you promise always to perform your duties according to the principles of academic integrity, honestly and scrupulously, critically and transparently, and independently and impartially?
Yes, I promise.
Then I present you with the diploma signed by the rector, supervisor and co-supervisor, and bearing the Great Seal of the Utrecht University. Congratulations.
Now I give the word to the co-founder, Dr. Swartz.
Dank u wel, meneer de rector. Dear Dr. Freeney, I'm the first person to call you that. Dear Saoirsé, when preparing this speech, I was going through my email archive to sort of look at when we had our first contact, and I can pinpoint the date. It's July 21st, 2016, so almost 5 years ago. And you sent me an email after your undergraduate supervisor at the University of Nottingham, Philip Moriarty, had passed on a job advertisement that I had sent him earlier. And a few weeks later, on August 3rd, you actually visited Utrecht for an interview. And the interview went smoothly, although I'm not sure actually how much you appreciated the restaurant we've picked, because we're not aware that you are a vegan, so my apologies still for that. But you also got along very well with the other group members. However, moving to another country was... to start a job is a big step for anybody, and also for you in particular. And you carefully considered all the pros and cons, but fortunately for me and for the group, you formally accepted my offer 1 week later, and then the rest is history, and here we are. You were supposed to create and characterize atomically well-defined metal molecular networks using scanning probe microscopy. And an attractive feature of those materials is that you can then control their properties in a designer type of way. However, if I sort of quote freely the Prussian General von Moltke, no battle plan survives the first contact with the enemy. And here, by analogy, you could say that a PhD thesis often does not exactly describe what was initially planned. And primarily, that's because the ideas that we as professors have, well, they aren't always correct, let's just put it that way. And the metal molecular networks turned out to be very, very difficult to synthesize, and it was even more difficult to isolate them from the support, which was critical for what we wanted to do. Now, then following the successful work by Marlou, we decided to use an alternative platform to create these artificial materials, namely CO molecules on copper. And you spent numerous hours, and I don't even want to calculate how many, down in the basement of the Ornstein laboratory to painstakingly position all these atoms one by one at exactly the positions where you wanted them to be. Now, as is quite typical for experimental work, it happened more than once that somewhere along the way the STM tip crashed or some other mishap happened, and you had to start all over again. However, so I can see that you actually recall that quite vividly. And the fact that you are an author on several articles not only demonstrates that you were actually, in the end, very successful in that but it also testifies to your perseverance and dedication. And those are skills, and I think every PhD student would agree, that those are essential skills to complete a PhD project, but I think they will also serve you very well in the rest of your career. During your time, you supervised 4 students. Some of them are here in the audience, Jan Jurre, Lisanne, Sam and Jaap. And I would also like to mention that you very successfully collaborated with a group of Professor Moret-Smith at the Institute for Theoretical Physics. And you also, sort of in a kind of roundabout way, also collaborated with Philip Moriarty, your former supervisor at the University of Nottingham. And the later project dealt with what you could describe as developing an autofocus option for scanning probe microscopes. And the pioneering work by Lisanne and you is followed also up by all the others in the group, and it will result in an extremely useful tool for future students. So also on behalf of the future students, thank you for that. I would also like to mention here your collegiality. You were always very willing to help other group members with their experiments and with filling the cryostats over the weekend. So that was, your input there was always very useful and very much appreciated. Now, fortunately for me, spending time with your colleagues in the basement did not mean that you take over all of the habits by the people in the basement, particularly the language jokes by the old-time king of pun colleague, who I shall not name here, but whose name is Peter. You did not take over too much of it. A little bit, but not too much. Saoirsé, it's not yet clear what your future will bring. You're considering moving back to London to start a career in the UK, but you're also seriously considering staying in the Netherlands. And I wonder if you ever thought that was possible 5 years ago when you considered moving to the Netherlands to start your job. However, whatever the future may bring, we as a group are convinced that you will land on your feet. It was a true pleasure to work with you over the last 5 years. And Saoirsé, also on behalf of the promoter Daniel, a well-deserved congratulations.
Very learned madam, on behalf of the board of the conferral of doctoral degrees, I congratulate you on the honors which have bestowed on you. At a personal note, I do hope that you can continue your interest in sculpting on the nanoscale, either in science or elsewhere. And on this, I hereby conclude the session. To conclude, I give the opportunity to the committee members to congratulate you. First, I would like to ask Professor Koenraad.
Well, I would like to share in the congratulations just passed on to you, and I would like to wish you all the best with all your plans in your life in the future. Really make the best of it.
Thank you. Dr. Fritz.
Yeah, dear Dr. Freeney, in line with the subject of your thesis, which is simulations on artificial, here's my simulated handshake to congratulate you. I wish you all the best for your future. You wrote a really beautiful thesis, which I think I will even pass on to students to read for specific things that I work on. And yeah, I wish you all the best. Yeah, good luck.
Thank you. Professor Dijkstra.
Yeah, also my congratulations with your very beautiful thesis and your just obtained doctor's degree. Very nice work, very nice review chapter 2 of your thesis. So congrats, good luck with your with the future, and I hope we will see each other very soon somewhere.
Thank you. Professor van Bladeren.
Saoirsé, also congratulations from me. I know you actually were looking forward to having a non-online meeting. At least there are a little bit of your group members in the room, but the opposition still had to do it online. But definitely I wish you a very good party tonight, which at least is partially possible. Also, good luck with deciding where to land your wave function next. That's not a simple question, I now understand. But it's probably not going to be, I heard, in academia, but in industry. So also good luck in finding a good position there.
Thank you. And then finally, Professor Meiring.
Yes, Saoirsé, congratulations. Like I mentioned, I've learned a lot from your thesis, and I hope that thanks to your thesis, I also pronounce your name finally correctly after you spending a long time in the group and me struggling with pronouncing your name. So congratulations on the PhD title, well-deserved, good defense, excellent thesis. I also like to thank you for your contribution to our group. You were a very strong social factor in the group. So good luck with your future, and I hope we'll meet again soon, either at the party or in the lab. So thank you and congratulations.
Thanks so much to all of you.
Thank you.